Okay, so I want to talk about, we talked about isomers, and now we're going to talk about chemical equivalents and non-isomers, things that could look like isomers but aren't necessarily isomers, because they're actually exactly the same thing. So chemical equivalence is for us to be able to look at a drawing and determine if the thing is the same or not. So these two substances are the exact same thing. The way I want us to think about this is that fluorine. Tell me what that fluorine is connected to. And what's that carbon connected to besides the fluorine? Okay, and now go to the next one. It's a fluorine connected to a carbon, connected to two hydrogens and a carbon. So I said the same thing. So it's the same thing. So go ahead and build it.
Carbon is red.
Black. Oxygen is red,
Oh,
typically.
what's that? I thought that was a massive bug for a second.
Good.
Yeah, I saw the corner of my eye rolling. I was like, what? It said,
That would have been consuming.
very much so. Should we use for chlorine?
Doesn't matter.
Okay.
I'd probably use orange or green or purple.
We're making just one of them.
One's fine. There's no real reason to put the hydrogens on. So there's that molecule. Right? What's the next one? That's it. So it isn't anything different, even though when I'm looking at it on the paper, it looks like, oh, well, it's on the top instead of on the side. Is it different? And it's not. And so why is it not different? A couple of reasons. One, I can just rearrange the orientation that I'm holding it. And two, we talked about this single bond a while ago. There's free rotation around the single bond. So the single bond won't fix any atoms in a position because literally as this is flying through space, I mean, it's tumbling over, but it's also, this bond is spinning. If it were quite cold, it would actually line itself up like this. Because each one of these would have hydrogens around them with electrons around them. So being like that, like this, those electrons on the adjoining carbons would be closer to each other. So if you offset them a little bit, then the electrons get further away from each other. Have you ever played that game at the carnival with the bowling ball and the two hills on the metal rails? You like push the bowling ball and it's got to go over the first hill without going over the second hill. It's sort of like that, like it here, and then it sort of pushes itself again and pushes itself again. Okay, so what we want to make sure is that we can identify molecules that are or are not the same. And more importantly than that, we need to be able to identify atoms on a molecule that have the same chemical reactivity. So every single one of these molecules is exactly the same. You okay with that? All I've done is I've held it differently each time. So now the question that I want to ask is, they each have 5 H's on them. If I was going to chemically react one of these molecules with something else that wanted to react with the hydrogens, would any one of those 5 hydrogens be more likely to be chemically reactive? Well, there isn't any opposite because it's a triangle, right? So I've got all 6 of these H's on here. Are they chemically equivalent? Remember that thing we did with there's a fluorine attached to a carbon. The carbon has 2 hydrogens on it. So do that with the H's. This is an H attached to a carbon with 3 H's on it. right? This is an H attached to a carbon with three H's on it. This is an H attached to a carbon with three H's on it. But what do I say here? This is an H attached to a carbon, and that carbon has an H and an F attached to it. So are these two things chemically equivalent to each other? This hydrogen, they're not. So if something were to come in and react with H's, it would either pick one of these two, which are the same, or one of these three, which are the same. But these are not the same. These H's and these H's are not the same. You okay with that? So you can design a chemical reaction based off of the equivalence of different substances. If I'm going to react with this carbon right here, one of these H's is going to react. It doesn't matter which one is going to react because each one of them is exactly the same as far as their chemical equivalents go. And it wouldn't matter because if I put something else on here, it's going to be the same no matter which position. But the other side, if I chemically react one of these two, it doesn't matter which one of these two, but it's going to be definitely different than these. So if I need to put something here, I need to make sure that whatever I'm using as the chemical reaction picks one of these two H's as opposed to these two H's. So I will say these two hydrogens here are definitely more chemically reactive than these three. Why? Because the fluorine here has a high electronegativity, right? Likes electrons a lot. And what we're going to find is that's a very important thing with chemistry. The H's right here, sorry, the electrons between this F and C, can you tell me something about it? So tell me about that covalent bond. Polar, right? Because the fluorine's charge is electronegativity is 4 and the carbon's is 2.5. So that's definitely greater than a 0.5. So that bond is polar. So what ends up happening is these H's here, are slightly more positive than these H's here because these electrons get pulled this direction, right? There's sort of a cumulative effect. And so because this carbon here is slightly positive, what's it going to do to the two electrons in the carbon hydrogen bond? Pull them towards it. So what you end up having is this fluorine is actually impacting all of the atom's electrons in this molecule, meaning the two electrons here that aren't a part of the fluorine carbon bond actually draw themselves towards the fluorine. So this is going to be slightly more positive. These guys will be slightly more positive than these guys over here, which aren't really going to show much at all as far as their a polar nature to them. Okay, so what is chemically equivalent in this, the second molecule with the two fluorines on? Everything, right? Symmetry is the easiest way to determine if things are the same. So I cut a line, it's a mirror image. So the fluorines are chemically equivalent to each other. The hydrogens are also chemically equivalent. Every single one of these four hydrogens is exactly the same chemistry. The two fluorines have the exact same chemistry. The carbons have the exact same chemistry because the molecule itself is perfectly symmetrical. And are you guys okay with that name for that? In that sentence right above? 1,2-difluoroethane. It's got two fluorines on it, so that's difluoryl, and the fluorines are connected to carbon number 1 and carbon number 2. You could make it a little bit different, right? We could make it, all right, so let's just, so here's my 1, 2, and then the other option to be an isomer would be 1, 1. So now this hydrogen right here is way more chemically reactive than these three on the other side. And now the only thing that has any chemical equivalents are these two fluorines. Everything else, well, I guess these three hydrogens have chemical equivalents to themselves. But it dramatically changes the molecule when you move things around. Okay, so why are the two red fluorines here not chemically equivalent? That chlorine is going to make that side of the molecule more negative. And so that means that that fluorine on the left is going to have a different amount of chemistry than the fluorine on the right. Why are those two H's that I have highlighted red in the middle one equivalent?
Position of the fluorine.
The position of the fluorine on each side is on the ends. Is there anything else that's chemically equivalent to those two red ones?
Or to the equivalent.
There's a lot of chemical equivalents, but these two red ones, we're already saying that they're equivalent, but these two ones, they're also equivalent. So all four of these guys have the same chemical equivalence. And then these two H's have the same chemical equivalence as these two H's. The fluorines are the same. These two carbons are the same. These two carbons are the same, but that and that carbon are not the same.
So it's just a matter of symmetry. Just putting.
You could just draw it and cut it. So me putting the F here is completely immaterial. I mean, if you want to make it easier on yourself, you can swap those and they can be very obvious how symmetrical. Just remember all that's happening when I move that F from the top to the left is the bond, the single bond is just twisted a little bit. Why are these two bromines not chemically equivalent? What's the easy answer? No.
Not symmetric.
Easiest answer is it's not symmetrical. Which one of those two do you think is more chemically reactive? Remember what we said about double bonds? The electrons on double bonds? Why are they more chemically reactive? They're not in the middle, they're on the outside. So which one of those two BRs is closer to the outside?
Right.
The one on the right is more chemically reactive than the one in the middle. It's sort of being shielded by this extra carbon group here. So remember what we were talking about molecular collision theory? Stuff has to hit, right? This extra carbon with the three H's is sort of blocking. So if something were to come in, say this direction to run into this bromine, you can hit it. But if it's coming in from this direction, you can't hit it because it's going to run into that CH3 before that. So it has more stuff in the way.
Does it get affected like electronegatively speaking at all by the chain or no? The bromine on the left?
This is more stable than this because there's more carbons and hydrogens.
Okay.
Imagine a molecule that's got like a bromine on it, but it's got 15 carbons. As a whole, that molecule is more stable than a methyl group with bromine on it because there isn't as much way to spread out the polarness of that bond. Okay, a little bit about cyclic alkanes. So the formula changes because now I don't need to cap the ends. So it's not 2N plus 2, it's just 2N. And so the reason it's like that is because the ends have come back around on themselves and reattached. So we can get rid of those two H's. But these are super common. We've shown the benzenes several times. Cyclohexane is a pretty common molecule, and it's a pretty common group that you'll find in different structures. We've seen cyclic structures in DNA molecules. There's a cyclic structure for glucose, fructose, all the sugars and whatnot. And the line diagram is just a hexagon. All right, so we're gonna go through and talk about the naming, the nomenclature associated with functional groups. And so the first one we're gonna talk about is the easiest probably, it's alkenes. And so when you see ENE, that's letting you know that somewhere in that molecule, there's a double bond. It could be more than one double bond, but there has to be at least one double bond. So let's say I've got a big molecule. Two, three, four, five, six, seven, eight, nine, 10. and there's a double bond right here. This is going to end in an ENE, letting you know that there's a double bond there. Even though most of the bonds in this molecule are single bonds. So how come the one double bond gets precedence over the fact that there are many, many more single bonds in the molecule? How come I'm not naming it for that? True, but the non-rotation isn't the issue.
Without that. Oh, so if we have one cycle.
I know what you're trying to say, but volatility, can't use that word here, right? Because what's that word mean? Reactivity. So we're going to start naming molecules, even if they're huge molecules with tons of single bonds. If there's one thing on it that's more reactive than a single bond, then we're going to name the whole molecule based off of that one thing. So what we're saying here is, even though I've got lots of single bonds, what really matters is that double bond, because it's going to react 1,000,000 times sooner than any of the single bonds. So I might as well say, hey, this thing is going to, its entire chemical reactivity is based off of the double bond that's there. That's the most important thing. So now we're going to, if I see a double bond in something, I'm going to name it for that, because when that thing reacts, that double bond will be the thing that's reacting. So again, ENE is going to be the end of it. So instead of it being propane, it'll be propene. Or instead of it being ethane, it'll be ethene. Or butane becomes butene. So we give a hard E sound on that E. We want it to be the shortest possible number, the smallest possible number. So we're going to count from whatever side makes it the short side. Why do I need, so this first example here, it's 4 carbons and there's a double bond between the first and second carbon. Why do I need 1 butene? Why do I need the 1? What? The double bond starts at carbon number 1. It must be going to carbon number 2 because there's no carbon 0. So when I see 1 butene, I think several things. First off, I think 4 carbons. Then I think there's a double bond. And then I have to think to myself, well, it's butene. So the double bond can be between carbon number 1 and 2 or carbon number 2 and 3. What about between carbon 3 and 4? Because that's really carbon number 1 and 2. Okay. So I can put it between 1 and 2 or 2 and 3. And so I've got 1 butene there. We're not going to talk about the cis right this second. Technically, the name of that second one is cis-2-butene. We'll get to the cis part. But the 2-butene should be obvious because it's going between carbon number 2 and carbon number 3. And so I'm naming it butene because the double bond is the most reactive part of this. Are we okay with that name of that third one?
Yeah.
I got to identify the fact that now there are 2 functional groups. One of them is a double bond and one of them is a alkyl halide. And so I'm going to put bute down because it's 4 carbons. I'm going to put butene down because it's 4 carbons with a double bond. Then right before the bute part, I have to say where the double bond is. And the double bond is from carbon number 1 to 2. So it's 1 butene. And then on carbon number 3, there's also this fluorine. So I'm going to write 3-fluoryl-1-butene. And then the last one there is 2,3-hexadiene. And so the hex is telling you that there are 6 carbons. The ene is telling you that there's double bonds. Diene is letting you know that there are 2 double bonds. And then the 2, 3 are letting you know where the double bonds are located. So it's telling you that there's a double bond between carbon number 2 and 3, and then also another one between carbons 3 and 4. That molecule is drawn for convenience sake, I guess is the best way to put it. Just to make it easier to see what's going on. 2, 3, 4, 5, 6. So double bond here, double bond there. So I'm saying that it's convenient for me to draw it like this, but it's kind of misleading. Why is it misleading? What else? What else is right here on this first carbon? Or last carbon? Carbon number 6. There's 3 H's there, right? What about right here on carbon number 5? 2 H's. What about here on this carbon? 1, right? 1 bond, 2 bonds, 3 bonds, 4 bonds. What about right here? None. What about right here? 1, and then 3 more on the end. Okay, so the first and 6th carbon are carbons connected to 4 different things. What's the structure? What's the molecular configuration around the carbon? It's tetrahedral, right? 4 things on it. Got to be a tetrahedral. So what about carbon number 5?
The one hydrogen one?
No, carbon number 5. So carbon number 1 is the one on the right-hand side. Because we get to the double bond first by starting from the right-hand side. It's the same thing. It's a carbon connected to 4 different things. So it's got to be a tetrahedral shape. What about carbon number 4? Trigonal planar, it's only connected to 3 things. So it's still going to be an up-down, right? As far as the structure goes. What about carbon number 3? It's linear. Why didn't I draw it linear? It's hard to see what's there, right? Like, did the person just accidentally draw lines that are too long? I mean, it's going to look like this. Right? Double bond, sorry. Did I get that right? Oh, I messed that up. No. It's proof that it's not, I can't like, but the issue is 1, 2, 3, 4, 5, 6. Like it that's not right though, right? Because that's 6 right there. Right? So I need to 1, 2, 3, 4, 5, 6. That's what's really going on. 1 here, 2 here, 3 here, 4 here, 5 here, 6 here. But it's kind of hard to see that. So instead, we just go with the up, down thing. So it's easy to count. And then you need to be able to look at this and go, oh, there's 4 bonds. It's doubly bonded on both sides. So that is a linear position. This is sp hybridized, sp2, sp2, sp3, sp3, sp3. Tetrahedral, 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 trigonal planar, trigonal planar, planar.
I think you can just, because you have the extra line for the double bond, you put 1, and then it ends where the carbon ends, and then you do another on the other.
Yeah, people do that.
Yeah, but that's not as fun, just up, down, up, down, up, down.
It's just,
you know.
it's just quicker to do it that way. Plus the can draw programs out there will be confused about that. And it also it takes up more space. So you'll see it most likely written like this. There's probably a limited chance that you would ever see it written like that. I've actually never seen that written in a book. So probably won't see that. But this also, when you see something like this, it's important for you to realize that free rotation between these 2 carbons, free rotation, I can't get spin happening here or here. And there's free rotation from there to there. So I get the molecule locked in place. That's going to change the chemical reactivity based off of the fact that that thing gets locked down in a particular orientation and can't have rotational movement around those bonds anymore. Okay, so then the next one, these are alkynes. So we hard I sound the Y. And so if you hear alkyne, you hear ine, then we're talking about things that have triple bonds. So same situation, I'm going to name it for the alkyne, even if there's a double bond in it, I'll be able to identify that double bond in another way, but the triple bond is more important than the double bond, so I'm going to name the molecule for its most reactive portion, given that triple bond in this case. So here's one butane. It's 4 carbons. The first carbon has 3 bonds to the second carbon. And again, this is not really shown structurally correct, right? Because this carbon right here has 4 bonds, 2 bonds, or 3 bonds this direction, 1 bond that direction. So this is sp hybridized. So this is actually linear up to this point. Next one is 2-butane. Do we notice anything different about this from the last one? There's no need for the cis thing. And we'll get to what that cis means, but it doesn't apply here. But again, this molecule is, this structure drawn like this isn't really what's going on. It's tetrahedral here, tetrahedral here, and then linear across this. So this whole thing is basically straight. The ends have hydrogens floating around in, but the carbons are all in a straight line because they're stuck in a fixed position. The next one is pretty easy. It's same as the last one, except I've got a triple bond on carbon number 1. So how come I had to draw the last one differently than I drew for the alkene? So it was 2,3 hexadiene here, and I can't do 2,3 hexadiene here. That carbon, if I had that carbon number 3, I had 3 bonds going this direction and 3 bonds going that direction, and 6 bonds to the carbon. Can't do that. So you can't have one carbon that's got triple bonds going both directions. You can't have one carbon that's got a triple bond and anything other than single bonds connected to it, because it's that's its 4th bond. Okay, next we're going to go over some aromatic nomenclature. So benzene rings attached to things. So benzene rings are aromatic, and that sounds like it smells, and it actually does. So that's where the descriptive name came from. The aromatics are any molecules that have these benzene rings on them. And so this, in this case, you use the benzene either as a side chain name or as the main chain, depending on its location on the molecule and what's going on, just to make it easier on you. It's totally up to you whether you want to use it as the main part of it or a side chain. So the first one, it's being acted as a side chain. So I've got 6 carbons in a row, so they're all single bonds on this main chain. So that's why it's hexane. And then I'm saying 2-methyl. On carbon number 2, there's a methyl group here. And then on carbon number 5, here, there's a phenyl group. You could say benzyl or phenyl. Either of those are fine for a side chain of an aromatic hydrocarbon or of benzene. So are we okay with this name? Does that make sense? Why did I count from the right side? It's sort of a grammar issue. M comes before P in the alphabet. That's why. So I could have counted from the other side and it would have been, 2-phenyl 5-methyl hexane, but P comes after N, so that's why I started with that. That's one of those silly grammar errors. If I had done it, counted from the other side, I would have gotten the same structure, that I would have drawn the same structure. And the alias of this is definitely the opposite. So it's not a terrible mistake. It's like your way to speak kind of thing. All right, so in the next one here, I'm treating benzene as the main structure. And so I'm saying that this is a benzene. All right, well, what's attached to the benzene? 4 carbons, but the 4 carbons are attached to the benzene of a carbon number 2. So that's why I'm going to call that guy second butyl. Is there another version? Yeah, it could be attached to the N. It could be just butyl benzene that would be attached to carbon number 1 instead of carbon number 2. But those are the only options, either attached on carbon number 1 or attached on carbon number 2. If they go to 3, that becomes carbon number 2. 4 is actually carbon number 1, just counted from the other side.
Is there a reason it uses like it's spelled out? Second butyl
What do you mean?
instead of 2?
Yeah, 2 would indicate which carbon on the benzene it's attached to. Sec is letting you know that we're attaching it to the second carbon on the butyl side chain. How else could I name this? Can you give me a different name? So in that second one, we're naming it for the benzene. But what if I didn't name it for the benzene? What if I chose to treat benzene as a side chain? How would you name it? Butane. 2-phenyl butane or 2-benzyl butane. Either one of those would be fine. All 3 of those would be fine for those names. Okay, so di-substituted benzene rings are a thing. Super common thing. So if I've got a benzene ring, many times in nature and in synthetic chemistry, I'll have just 2 things attached to the exterior. We've got lots of different ways to name these things. So obviously it's 2 carbon line, 2 joint on each of these. So my positional changes are they're 1 carbon away from each other, 2 carbons away from each other, or they're 3 carbons away from each other. If I move this over to carbon 5, and then the same thing as this one here. Move it over to carbon 6, it's the same thing as this one here. Okay with that? So there's only 3 ways to put 2 things on a 6-membered ring. The names that we have for that are either ortho or pro or 1-2. So this is 1-2 away from each other, or they're orthogonal to each other, meaning they're right next to each other. So that's why it's ortho or pro. If they're not right next to each other, then that would be positions 1 and 3, which is an acceptable nomenclature, or you can call it meta. So meta, they have to have a carbon separating them. They can't be right next to each other. And the last one is para. So they're on opposite sides of the molecule. Then side chains attached to a benzene ring. These are like in the same way that we name water. H2O can be cold water or it can be dihydrogen monoxide. We've got names like ammonia or acetic acid. All of those different names, those are common names for things. We have some common names for these different benzyl functional groups things because they're super common. So the first one's toluene, then phenol, styrene, benzoic acid, benzaldehyde, and aniline. Those are all names we have for functional groups that are attached to these different benzene rings. Have we heard of these names before?
Yeah, that's what I remember. Polystyrene.
So that's the monomer for styrofoam. So when you've got styrofoam, it's these things over and over again. This is one of the parts to the big white mint in the urinals. It's puts off a scent that masks urine and kills anything that might be in there, which is not a big deal since you have to be pretty basic for your urine not to be sterile. How about this one? Modeling glue. Building little car models or airplane models using polyurethane-based glue. Benzoic acid, have you seen that? It's a very used food preservative. Same thing with the benzaldehyde, so you might just see that written on the side of a product. And it's probably not the last one there, but those are the common versions. Monosubstituted substances on these, let's get the benzene rings. Do you remember me talking about the delocalization of the electrons on the benzene rings and why benzene was dangerous? It was like a Chinese throwing star, right? So it can cut through stuff that's non-polar, because it itself is very non-polar. And it can actually alter DNA and cause disease because of its nature. But the moment you attach something to it, that changes. So if we go with like a Frisbee analogy, you can throw a Frisbee really far. But what if you, I don't know, took a roll of duct tape and then just taped it with the roll still on it and tried to throw the Frisbee? Not going, right? Even if it's just a piece of tape, like 6 inches long piece of duct tape, and I go to throw the Frisbee, it's just gonna flop and not go on. So the scariness of benzene becomes not scary the moment I attach something to it. So all of these things aren't going to be doing the benzene chemistry because even though that thing's there, it doesn't matter because now there's something attached to it. This drives me crazy when people send me, is this a real thing? Videos like, oh, there's this thing called benzene attached to this molecule. And benzene is, carcinogenic, a known carcinogen. I'm like, well, that's a known carcinogen, but that's not. That's a known carcinogen, but that's not. So it matters. Like if the thing that is terrible is attached to something else, it ain't the thing anymore. It's just not the thing, right? You okay with that? A handgun where somebody has taken like super glue and just squirted super glue into the barrel isn't a handgun anymore, right? It ain't the same thing, doesn't matter. So same situation with all these things. They are not the same thing the moment I've attached something to them. They've got this anchor on. You want to go grab something, but look at that last molecule. Does that name make sense?
You guys look at the lab pictures beforehand or no?
It wasn't supposed. I don't think they're not there. Well, we have a lab nine that's due at the end of the week, but like, it wasn't. I couldn't download it. It's like, okay.
I'm moving off hopes and dreams that have been in it today, I'm gonna be honest. I'm going to bed today. Okay though?
No, I just got up, took a shower, got in the car, and drove here. I will never be able to remember that.
The one on the right?
Yeah.
I mean, half of these on, but
Is that these things?
yeah, it's TNT.
Yeah, sure.
I had no idea there had benzene.
But like, I see the totally part, but then, like, yeah, but I guess then we have just. Picture them.
So
Okay.
we're starting on the top left, night.
Oh, yeah, that makes sense.
Is energy nitrite?
So it's a tolling. With 3 nitrogens. Three nitrogens. It's actually, mononitrogen dioxide. Thank you. Yeah. Yeah. But we call that nitrogen. We call that nitrogen. I don't know why, you kind of think of the nitrogen, it's like, oh, the nitrogen. No, it's a little more. More.
Does it even mention stage 3 at all?
No, it's because it's totally to the end.
It's a carbon yield.
So I guess if it's. Nitrogen. Good nitrogen, it's really having. It's going on, but I don't know how the nitrogen supports that, and oxygen's like the carbon bond. Doesn't have like. No, it's nitrogen, typically has 3 bonds in front of it, but the oxygen, which shows oxygen bonds too. Don't worry about what, I thought the nitrogen can have like stupid amount or something. Right, no, I think it's like. It's phosphorus, phosphorus and another, aluminum.
So wait,
No, I think it has 3, it's fine.
how does King explode? Is it heat activated?
It's like.
Yeah, it just needs, it needs to be able to decompose. That's all,
Right.
most explosives are a decomposition reaction. So an explosion, the actual like dictionary definition of an explosion is the rapid expansion of a gas. So what I do is I take a bunch of molecules that would prefer to be gases like N2, O2, H2, and take them and let them do their thing. So we heat this thing up and it will convert itself into O2 and H2 and CO2 in this case, and get much bigger since the density of the gases is like 1,000 times less than the density of the thing that you're turning into a gas. So if we've got an object that's this big, it becomes 1,000 times bigger. And it does that in an instant. All of a sudden it's taking up a lot more space than it was. So N2s attached to benzene rings, we can call those nitros. So that's why this is trinitro-toluene. Because there are 3 nitrogens on, NO2s on there. But if I cover them up, what do I have? I've got the toluene group with 3 NO2s attached to it. Who invented this? Alfred Nobel figured out the best way to take this and make it portable. Anybody know what he did? Turned out to be like, oh, well, that was it? That was all you did?
There's candle ones.
No. Even easier.
Like it in something, right?
No,
Right, yeah.
nope. It's a gooey, syrupy like liquid, the nitroglycerin. But it's unbelievably unstable, like literally that might cause it to explode. So you're not gonna want to transport that around. He literally just mixed it with a bunch of sawdust.
Wow.
So imagine mixing honey and sawdust together, except the honey will explode and that stabilized the whole system. The real issue with dynamite, the only issue with it is it needs to be kept dry. If there is moisture around, then the nitroglycerin will actually come out of the sawdust. So, and it's super easy to tell if what you're looking at, if the dynamite you're looking at is dangerous or not. Does it look sweaty? If it does, then get the hell away from it. It literally will explode if you breathe on it. So all he did, literally. I mean, obviously it was super scary initially, right? He doesn't want this to explode in his face.
Starting a pot.
And he made so much money selling dynamite, selling how he did it. And just initially just the manufacturing it and selling it, you know, he turned it into a foundation. And that foundation was the Nobel Foundation. And so that organization makes so much money off of investments that it's able to, you know, spit out I think it's $1.7 million per person or per award, and still make more money. So I want you guys to do the one with the benzene rings on it. You guys feel free to work together, but name those, was it 6? I'll pull it up here.
This page with the ABC.
The page with these benzene rings on them.
Oh, okay, practice problem. That substituted aromatic.
Dye-substituted aromatic. Yeah, this guy.
There are different rings other than benzene, right? It's not following me.
Oh, yeah. We can. Yeah, you could substitute in oxygens or nitrogens and have heterocyclic rings. It could be bigger or smaller than 6. It's just this is by far the most common structure because of the bond angles. That 6 carbons gets all the electrons just the right distance away from each other to make them happy. What do you got for the first one?
Paradise, bromo.
Yeah, pyridibromo-benzene. Is there another name you could give it? P, dibromobenzene. What's the other one?
1, 3, 4.
1, 4. 1, 4. Yeah.
So there are,
Let's see, 6 names for the second.
Great. That's great.
It's ammonia.
Are the ortho meta para, is that for when they're the same only or just the spacing in general?
That's for the spacing.
Okay.
When there's. So that one might be.
Meta?
I don't know. So next to those two. But I believe.
What's
I'm willing to bet that's correct, dude. So there's 6, that's probably right.
meta something benzene should probably call it.
That whole 3. Actually, yeah, that would be. I'm gonna write meta. Phenyl, halide.
What is found in just that group?
Yeah, it's
Trying to remember what phenol is.
phenyl is the one.
Well, phenol is just the functional group that basically is one of these,
Yeah.
but in this specific.
Oh,
case,
phenol is OH.
Phenol. Instead of bio, it's.
So phenol is just a benzene with the alcohol.
Yeah, it's-
Alcohol, what?
Yeah,
yeah,
it's the
it's having
OH
a
compound.
combination.
Oh, right.
It's like
What do you guys say? Meta phenol?
sulfates for an alcohol. So here it's literally.
So we could just call them booze.
Yeah, exactly.
What did you guys put?
The first one I wrote was meta phenyl and covered in things.
Aniline benzene?
Can't say it, dude. A and I is like.
You could also say it's. 3.
Yeah, that works.
Right there. Or you could say it's phenol 3. That's also a possibility, assuming that one would be the position where the phenol is.
Well, I mean, I guess, oh wait, no, it's alphabetical.
Or you would say one something, three something?
Actually, I would say it's handling 3 phenol.
Yeah, that doesn't sound as good as.
Phenol 3 and. It's been a whole lot. Good, bad, it's fine. It's right there.
Benzene,
I don't think it,
does it mean benzene?
no, because it's a specific group, so we didn't say that.
Oh, and, yeah.
So you have this.
Are we sure aniline would come before though? Is it still then? Real now? Phenyl aniline.
But I think that's
But I
only
never
if we
done that.
say that, like, this is on this carbon. those things.
Well, actually, no, I guess in this case, like this could statement, you would go with, this doesn't really matter. It's first.
Yeah, but phenylalanine sounds so much better than
Now, three,
no.
gotta be specific.
Gotta be specific. No, because if we put the 3 in there, then we have to do it backwards, so it'd be 3.
Huh? So you think actually,
Oh, because we'd be,
Can the 3 go on either? Does it
Yeah.
matter?
well, it has to be three because it's 1, 2, 3.
But it could go on phenyl or anim.
Yeah.
That's-
Because it's just the distance they are, the one that you apply first, I think, and say it's the main one, it's the one that's positioned at that action. At least based on how long this, written. That's what it is.
I guess
It's name is all like, okay, so where do we? It's like, well, if you look at the implications.
I guess that means that since the phenyl is at the top, that one's number 1.
Unless you go with this.
So we turn sideways.
Yeah, this is
The-
where,
the
this is
OH
where
would be on
it does
4.
work. It's the pattern. So you just do out better.
But then it'd be, what would that be? It'd be,
And the 1 and 3.
no, it'd be 4. It would be like this.
No, it's not 4. Well, if it's 4, it's gonna be all the way across.
Oh,
Or
right.
it needs to be, 'cause you can go either direction. No, no, we can go either direction.
What was the one side that
If
said?
you're talking about 5, you're actually talking about.
Oh, okay, whatever. I'll just let you figure it out. I don't know what we're doing.
See, dopamine like paired with adrenaline and something else too, right?
They all are
Serotonin.
basically the same.
The
Not really, but like they have the same function.
catecholamine was that
Yeah.
the?
They both have benzene.
They're all this one thing, with like.
But they have the ring structure. I don't know if it's this, but it is a.
We're screwed.
They're all the same.
All right.
With like key differences in. Well, kind of, they all play some.
What do we want to do for the OH one? Have you guys already done this but not paying attention or? The next one,
Oh,
I'm thinking, should we run para or should we do that?
All right, better.
I'm thinking 4 hydrox to. Because I mean, think about it, dope, it's got 2 of these hydroxide. They didn't mess with this.
That's what I hear. We're just like, okay.
Or is it 3, 4 dihydroxide? No, then liquid. 3, 4 dihydroxide. It's the dope.
Through that.
Para, toluene, aniline? Oh, no, it's phenyl. That didn't seem right though, but
You got the second one?
we have a
I
few,
don't think so. What you got?
what should we do first?
I'll let you get it. It's not it. I have mine.
What's the first principle you need to consider when naming these?
Well, we tried to do meta for number 2.
Yeah, that's fine, but what do you need to consider?
The alphabet?
No,
Is it like the suffix name, the prefix, verb suffix?
nope,
Does anyone apply for this?
nope. What is it? The benzene, right?
Yeah.
So you could name it something like,
hydroxyl group. Okay, so it's redundant if we put aniline instead of hydroxyl.
yeah.
Okay.
So what I'm saying is, you could name it for the aniline, right? What else could you name it for? You're okay with those? So then you could also put down 1,3 for both of these. You could also write meta for both of these. What's the other thing you could do? You could say. You could also do that. You could just say, hey, this is a benzene. And I've got an amino and a hydroxyl group attached to it, and they're meta to each other. So there's actually 7 ways you could write this. But what's important is that you can come up with one. That's what's important. Or, given this, can you draw that? So you'd have to know what a phenol was. So then you draw this structure, right? Draw the phenol, and then you go down 2 carbons to get to the meta position, and then you draw the amino group. So going either direction is important, but being able to come up with all 7 names isn't important. But given any one of the 7 names, you should be able to draw the structure. Does that make sense?
So for the next one.
Yep.
You could go para-hydroxyl toluene, right?
Yep.
But if you wanted to do it that other way, is that just a carbonyl? What do you call the?
Methyl.
Methyl?
It's just a CH3, right?
Nah.
Yeah. And then you could also call it para hydroxyl methyl benzene, or 1,4.
I think you can do these now with their precision. What was what's the next one? Was it ortho? Is it-
While you guys were arguing about these, so I was like, screw it, I'm
calling it
1, 2.
What?
God damn it. I don't know if we ortho and a pair with the numbers,
How do you spell oral?
What? CHLORO, what are you doing? It's like chloro, chloro.
CH what? LORO?
Yeah.
Fluoro. It sounds like I'm saying Carl in a deep southern accent.
Ortho benzene.
Oral. Orthodichloro. Okay. Oh God. Double bond. Wait, what is that?
That's a styrene.
Oh, boy.
Styrene. Styrenes. So we can call this, I'm thinking. What was 2? 3-ethyl styrene. Oh, that is 2. Yeah. Okay. That's fine.
Oh, we have
I'm
a,
still gonna write meta.
we got a chain. On the other one, it's long. What are you guys writing? It's like the CH3CH2 is a little long.
Yeah, that's an ethyl chain. So 3-ethyl
Just 2 carbons.
Wait, we said,
No,
we
this
say
one.
3-ethyl stack. We just skip the ethyl chain to the styrene.
No, you can say.
Because what we did there, they didn't go like. It's like an email, where there's usually a particle word. No, it's not. Amino.
Amino is just describing the. What's going on? Actually, two hydrogens. What do they call the?
We don't like meta-ethylstyrene. We don't like that one. Oh,
Three methyl styrene.
Well, that's what.
Yeah, see, so we're done.
Like, what else? What about like the other way?
Oh, it'd be. If it's one, no, it'd be.
Because I don't know. Triple bond.
Meta, ethyl, methylphthalate.
Yeah, exactly.
Wouldn't it just be dimethyl? There's. We diethyl.
It's,
So it'd be, three ethyl ethene. Sorry, no, benzene. So, because it'd be one and then two. So if it's like the alphabet, that means we count
Oh,
up.
we would just say 1, 3.
One,
ethyl
three,
ethene.
ethyl ethene benzene. I'm gonna write it. Why are you laughing?
I'm past my breaking point. So for
Here we got some food.
food,
I don't. I'm trying to pick out these.
is,
Unless it's the coup.
isn't that benzoic acid?
It's so that would be.
Yes, it is. Yeah.
Parafluoral. Wait, floral?
Wait. Is it benzoic? Because on this diagram, these two oxygens are attached. So over here, it's double bonded.
Yeah, but the thing is, can those two oxygens be the
I mean,
that would be a rock center. Is that gonna happen?
well, no, because they need to be,
Is the oxygen light being like that, or is it gonna be like the zone stuff?
I think there had to be a hydrogen in here. There would have to be a hydrogen in here because then these are oxygen. No, there had to be another one. Oh, the carbon.
This one, we got it. Carbon, two oxygen.
No, I think
No, but
it is
you-
benzoic.
If the O's are next to each other like that, that means both the O's are double bonded to each other and the carbon and the hydrogen, so there need to be two other hydrogens, I mean,
Isn't
to
it
make
just,
up for the. So the carbon has four bonds.
isn't it just separating the hydroxyl group? Isn't that why it's written like that? Because it's an acid.
Well, for the carbon to have four bonds here, it would have to be a zero bonds.
So what I'm gonna do is I'm gonna write para.
That's the pair?
I'm just gonna write para. Fluoro.
Flora is what I went with, but I didn't know.
So, yeah.
All right, that sounds good. That's a bit of chain there.
Probably wrong.
No.
That's a 3 chain, which is what it goes med, F, and then prop.
What are you looking at?
No, I'm trying to recite it in my brain, the order of. So in my brain, I was looking at the image, the mental image.
I'm pretty sure we got that one.
No, that was,
I don't think so.
and a lot of papers here, it's a lot of loose change.
Oh, it's good. It's the same.
This one.
This meta again? N? Or
Oh,
Yes.
meta, and
But that doesn't follow the alphabet.
oh, bro,
separate.
meta. Is it bromide? That sounds wrong.
Bromine.
Wouldn't it be bromo?
Bromine. Could be bromo, since it's just.
Bromo.
Bromo, benzene.
Yep, it can't be bromide because it's not an ion.
Okay. Bromo is silly though.
Bromo is silly.
No,
Yeah, bromo.
I think I picked bromine for a presentation and like most of just because it had brom in it. That was like my whole thing.
I think you have to sit there and realize, oh, wait, an accidental error.
Yeah, it's an actual element that does the,
That's-
easy, aniline. Or. Oh, it's redundant A's. This is fluoroaniline.
Okay. What?
What have you guys been putting?
It's whatever element it is add an O.
Oh.
Sometimes you can throw some Y.
Or, oh,
And it makes it up. So I said, so I said, rolls off. Yeah.
English. Sorry, American,
American
the
spell.
American language.
And we just looked at that one, so we know that. Okay.
I already, I didn't write it down. I can't. I failed. Well, 2, 4, 6.
Friday nitro. Oops. 2, 4, 6, Friday nitro. Now both go actually remember that. Yeah, you're right. We did it somehow. I'm willing to bet the first 3, we went over this. Those are probably correct. I think the rest of these 6. I'm not feeling it. The last one, yeah, we looked at it.
I think there are, we have 100% here.
I don't.
Full confidence.
All right. Give me that first one there on the upper left.
Who wants to go here?
Not being.
Okay.
We'll go in a little circle here.
Ortho dichlorobenzene.
Love it. Anybody else want to throw anything else in?
We did one. So
That middle one, Grayson, what's the next one?
Are you gonna do the benzene one or this type? We have the style.
Done?
Okay, I said. Para, fluoro, benzoic acid.
Next one?
I guess we'll just do a rotation here. Meta bromo propylbenzene.
It's a
Propyl.
yeah, that's it here. Love it. And then that last one.
2, 4, 6, trinitropylene.
Toluene.
Toluene.
Nice. All right. You guys are all disubstituted aromatic nomenclature experts. Let's do,
The captotrol is the benzene. In adrenaline and dopamine, they it is a benzene. But with 2 OH. things.
That's what I'm saying, we smoke good.
all right, pull this one out. I gave you guys, I think, 4 worksheets.
It just looks funny written out, not with the lines.
Oh.
So do one and then we'll go over 1A and B.
Okay, wait, let's do B first.
Okay.
He was easier. In my opinion.
Oh, man, did I write that wrong?
Why don't we just go like, what is it, 1, 2, die? That will then
What were you guys doing?
be, 1 B. The funny,
But that's not bending, there's happening on.
I thought it has that,
Yeah, that's like, what am I thinking of?
isn't this how it's stable? What has a bromine?
No, it's not.
There's a bromine.
Yeah, it's double high. Isn't that cyclohexane?
It is.
Yeah, because benzene can't have hydrogens on it, because they're well, you know,
Well, it has
it can have 1 per carbon, but it can't have 2 per carbon.
Why not?
It'd be benzene.
Why can't it have 2 per carbon?
You wouldn't be able to have the double bond.
But you don't see any double bonds there, right? Plus, what's the name of this worksheet? Okay.
Well, back to this, my brain is.
I know there's a 4 bromo.
Are we,
It's like, I just started from shortest side, I'm like, whatever, 1, 2 people. That's 3. Maybe we're starting from there, yeah.
I'm just gonna write it so it's straight. It's my strategy here. Okay, here's an end right here. See.
Let's go on the right, 1, 2, 3.
Where this card,
Starting from
this card's attached
the
to
first
3.
carbon on the right, and then we go down to the bromine, to 3.
This is how you do it.
So it would be. Red. 1, 2, 3.
Go back to A. I thought that was what we were doing before. So am I wrong to say that Atlantis is 10? In A, because you can. That's the longest length of carbon, right? If you go like,
Yeah.
in a jacket,
Wait, where's
so
the
deca. For 1A.
I see the long exchange in the state.
I'm going zigzag,
No, it's the.
top left to bottom right.
This from here to here. Oh, you're finding, okay. Because there's. Oh.
Deca, and then we have a lot of what's over here. Where do we count from it? Both 5. The bigger,
Probably the shorter from.
so 5, 6. 5, 6. Oh. Methyl, and then. Methyl butane. Huh?
5.
Oh, 5 methyl.
5, 6. So we got 2 things on that.
Oh, there's bromine too. Yes.
That's the
doing
first thing
so
I
good.
saw, it was like, it was like carbon.
Would, okay, I was thinking like. Decane, so 5-methyl 6-butadecane, but that's like without bromine in there. Look at the
No,
picture.
you just add bromine.
Ethyl decane. So we use 5-methyl though, right? That's locked in. That's easy, 5-methyl. And then is bromine part of the is butyl? What is the O? Just there?
5, 5, 6.
Wait, why are you doing 5, 5?
We got 2 things on 5.
Wait, which way are you?
Oh, you're going bigger
This way
there.
or From this one.
Are you going 5 butyl?
From-
Isn't it 6?
Oh, so you're starting with broke, okay, I see what you're doing.
Always like splice them up. So it could be 5, 5. From purple. 6, ethyl,
5, 5, bromo propyl,
yeah.
6 butyl. It's a butyl.
How are you doing?
You do it over there.
Wait, I'm tripping methyl, sorry. Methyl. I was reading some random. Benzene.
You said. Bromo?
Wait, it's not even, we're out of
Are you guys done with A?
decane. Okay, sure, let's try it, okay.
You pretty sure?
We saying 5, 5 bromo propyl, that's what we're saying?
So,
6 methyl decane.
so what I like to do with these is, first off, you guys had a little hesitation as to the length of the molecule. Sorry. Right. So there's your what?
Okay.
There's your decane. All right. So everything that I've run a line through has been named. So what hasn't been named? This, and this. So what are those? Propyl. Bromo. And methyl. Okay. Then it's got to be alphabetical. Right. And then I have to designate the numbers. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So it's going to be starting from the bottom right-hand corner, because that's going to give me 2 5 numbers as opposed to 2 6 numbers. So the first one is going to be 5 bromo. Then the next one is going to be 6 methyl. And then it's going to be back to 5 propyl decane. That work?
Is that alphabet? Is that why it's
That-
in order?
BMP.
Okay.
So what I really like about these names is they're incredibly utilitarian, right? Everything that's written there is written there for a really specific reason. There isn't any like English BS where there's silent this or a GH makes a different sound. It's like that thing is because of that. And this thing is, you could directly tie that 5 to that. This bromo goes right there. Like it's all very specific. Going backwards makes it really easy. You'd start at the decane and just draw 10 carbons in a row. And then you could pick any one of the side chains, 5, go 1, 2, 3, 4, 5, and then put a BR there. And then 1, 2, 3, 4, 5, and put a propyl there. And then 1, 2, 3, 4, 5, 6, and then put a methyl there. Very, like, this is what you're doing.
Okay, wait, I think it's B now.
Okay, so what is the structure? It's a cyclohexane, not a benzene, no double bonds. Carbons have multiple H's on them, so it can't be a benzene. So it's a cyclohexane.
It looks like a like a sigma symbol, right? Isn't that what that is?
I don't know what you're talking about.
I drew a line around for it. It looks like the thing, or whatever. That Greek symbol. Is that not real? Am I?
What are you talking?
You think that looks like a sigma?
Is that what it's called? I swear there's a symbol that looks like this.
The omega kind of looks like that,
Omega? Okay.
like for the ohm. Are you talking about this? Oops,
Yes. Yes.
yeah, that's omega.
Okay.
We're not a big-
Okay,
So count the carbons.
so what are the side chains on this ring hexane? Two methyls and a bromine, right? So bromine gets alphabetical priority. So I'm gonna say 1 bromo. And then 2, 3. You good with that? Gotta have the commas between the 2 and the 3. Not dashes. And we need dimethyl, even though that's stupid, right?
What is cycle for again?
The fact that it's in a ring structure comes around back onto itself. I don't know why they added that prefix to the multiple side chains that are the same, because I wrote 2, 3, so that obviously is indicating that there are 2 of them.
Yeah, I did mine weird. I don't even know what I was. Did 3 bromo octane. What? I
No.
just counted.
There are 8 carbons there, but so you wrote decane for the first one, right? How come you didn't include these 3 and this 1 and make it 14? Because it didn't make any sense, because it wasn't part of the chain. So this is part of the chain, and we're not allowed to like go out and then come back in. Like these are cul-de-sacs. So you can't go out and come. If in some way it goes out and then reattaches in another spot, then that's fine, but it doesn't do that. Can we draw 2A here?
No, F is 7. We're good.
F is 7.
Yeah, so like, we could totally do this one.
What? Okay, are we gonna do the line thing?
I am.
Yeah. Right at carbon, hydrogen, carbon, hydrogen.
Alright, so on number 3. You got another 2. You got number 4. You got 1. So 2.
And then, so which side are we starting from, left or right?
Don't matter.
Left side.
All right, we're doing left to right, because that's how we read.
Oh, actually, I'm sorry, so it makes me better.
So 3 is 2.
Every time.
No. Wait, what?
3 is a 2 thing.
Yeah, 3 is
2 things, and it's 2 1 things.
Going out the other way. Or does it matter how you draw it?
Well, there's 2 ways to go.
Just gonna make a little V.
So,
That's it. That's it. Isn't it?
Matter of fact, we should probably do the beach with icon on the top and bottom. We should probably do the beach.
I mean, I don't know, it doesn't matter.
I was like, no cares.
How Lions here?
It's all spinning anyway.
It's all spinning.
It's all spinning, right?
It's just boring. Perfect. See how it-
I mean, we could just draw a straight line, because I mean, that would, at one point, the orientation might be like that.
You just have to.
Yeah.
You just got a straight line.
Just put some blotches, like, this is, It's spinning, so it's blurred.
Yeah, we're kind of straight. Yeah.
okay, so it's a
Wait,
hexagon.
so,
But here's the thing, it's a cycle of pentane.
So it's
And
1, 2, 3, 4, 5.
something about it is propyl and the weird propyl.
It's ISO.
Now, these are attachments, right? So we can write our
No, but we
pentagon.
know that propyl means
Well,
3.
so I think we have, so we have like.
Yes, we have pentagon.
Propyl is 3.
Cyclopentane is 5.
What is iso? 4.
3, 4, 5.
Okay, so we have a pentagon,
Yes.
right?
Hmm.
And then,
On number 1, there's a bromine.
I'm not.
Where is our one? Does it matter?
That's putting it on the top.
Wherever the bromine is, it is.
Okay, we'll just do the top. Yeah.
Number 83,
On there is
which is the
a
bottom
weird
right.
propyl, so I think that means it's like.
What are you saying ISO is?
Well, so like a normal propyl, right, you know, it's 1, 2, 3, but if it's a weird one, it's down. 3. So
Okay.
2 and then 3 off to the center, but I think I'll be able to read propyl with it.
I will trust your.
So 2, 3, 4, 5, 6, 7.
Yep.
1, 2, 3. So 1, 2. And then 1, 2, 3, 4. We're good. Cyclopentane. Weird. There we go. Pentagon. And then BR on number 1. And then 1, 2, 3. Isopropyl.
Oh.
It's ISO. Not connected to the end. Connected to the middle.
That was quick thinking. Oh, that one. So,
Oh, that one wasn't gonna be a naming. Did I give you,
Quaternary carbon.
yeah, we haven't talked about that yet. Did I give you this one?
Yeah.
Okay.
One and two.
1 and 2. Electron dot structure. Oh, what is that? What is it?
Well, that was the perfect, what is that? That's the room.
What are they?
Isn't that just, like, we just have to put a bunch of dots on it? That's a lot of on the dot.
have carbon with 1 dot on each side. Then we have another carbon, 1 dot on each side. Merged together, so we got 2 dots in here. Now we have a hydrogen, remaining, fill in the second dot, everything.
Works for me.
I think that's
I'm gonna say that's probably correct. Or it could be the,
Yes.
or he wants us to do electronic.
So it's a little dot and it's encompassed by a big one? A big circle?
No, just put 8 dots around the carbon, and then everywhere there's 2 dots. Put a hydrogen. Like range or things.
Name the compound.
Yes. That can be position. At E, state the hybridization. It's the SP, there's 4.
Yes.
Right, and there are like 4 single on the same.
Maybe the geometry of the carbon is linear.
Easy tetrahedral geometry.
Oh, I was about to say, what are you saying?
I still get 1.
The
Will we
geometry of.
just
Yeah, that's
tetrahedral and then
What's-
Technically,
Well, no.
part of it is tetrahedral, but to each other. Well, and
To each other, they'd be linear.
the geometry between any 2 parts. Even if it's in the situation.
Somewhere in linear.
The carbons themselves are tetrahedral. Because the sp3 hybridization is.
So they'd be tetrahedral to each other.
I think so. To each other, it's always a straight one between bonds.
but it's still like 4.
Yeah, so it's name the geometry of the carbon. Is that carbon to carbon or just as they are? Like,
The geometry of each carbon, which because it's sp3, it's tetrahedral.
or about. Whichever one is wrong, I'll cross out.
Oh, that's what the dot structure is. forgot what the dot structure was, so I had to literally, I was gonna have to look it up to figure it out, sometimes it's not it, I don't know why.
Yeah, that's what I said to do.
Alright, so it's, instead of lines, it's just dots,
Yeah.
and then it's two,
It's two dots.
two, okay. Yes.
Something.
Are we on two now? The,
Wait, but let's check our answers first.
wait, this is messed up, it's said in two different ways.
Okay, so you were correct. So that's good.
1, 2, 3, 4, 5, 6, 7. Which one did you? For 2A, they're both 7, if you go both ways. Let's just go straight, I feel like. Is that easier or no?
What the hell are you guys counting?
You're
Yeah,
counting,
let's just do both math balls and,
Yeah, because you can, you can put the brown.
he's counting this as 7 as well.
Oh,
heptane. And then we'll just, whatever. Methyl bromide,
but no, you start with B, so B would be number 1.
bromomethyl heptane.
One, brown, two, methyl.
One, so 2 bromomethyl.
No,
What?
No,
B two.
wait, which one are you guys doing now?
That's 1 bromo.
tell me why the yellow is a bad route to take.
Oh, why?
Because then the,
The
we don't know
bromo,
what the.
Because then the side chain has a side chain.
yeah, and then it's,
Does that make sense?
that's.
I mean, there is a way to name the bromine side chain onto a side chain, but we don't need to.
That's what I was encountering, trying to do that, I was, yeah. That's right. One bromo. Methyl,
Yes, sir.
butane. One. Four.
Seven, 1.
All right, good. So I just pass out the lab